Exercise 9. Two identical springs, each of which is characterized by its empty length L0 equal 20 centimeter, L0 equal 20 centimeter, and its stiffness K equal 25 Newton per meter. So K equal 25 Newton per meter. The two springs have the same horizontal axis, x prime x, and intercalants between them. A punctual mass m equal 400 gram, from gram to kilogram times 10 to the power minus 3. It's equal to 0.4 kilogram. In physics, the SI unit of mass is kilogram. O being the middle of the segment AB, with AB equal 60 centimeter, it's equal to 0.6 meter, from centimeter to meter times 10 to the power minus 2. Part 1, it is neglecting friction, so friction equal to 0, and we take the gravitational potential energy of zero gravity in O. This is the reference. Calculate at equilibrium the potential energy. This is part 1. The potential energy of the system as system Earth spring M support. So, at equilibrium, O being the middle of the segment AB. So, the length of each spring is L equal AB over 2. So it's equal 60 over 2 equal L equal 30 centimeter. Then the elongation of each spring is delta L equal L minus L0. So it's equal to 30 cm minus 20. It's equal to 10 centimeter equal to 0.1 meter. Then the potential energy PE of system equal PE of spring 1 plus PE of spring 2 equal GPE1 plus EPE1 plus GPE2 plus EPE2. Why the springs on the reference? So GPE in the two springs are equal to 0. Therefore, we obtain half K delta L1 square plus half K delta L2 square. It's equal to K delta L square, since delta L1 and delta L2 are equal to 25 times 0.1 square equal 0.25 joules. Part 2. We place M at the point I of abscissa X equal plus 5 centimeter. Then the solid M is placed to the right by 5 centimeter. First, the spring it's O. suppose that this is the empty length L0 and this is the empty length L0 and this is delta L, and here delta L. After we place M at the point I of abscissa x equal plus 5 centimeter, then M it's placed to the right by 5 centimeter. The figure become like this. This is L0, keep the same. This is delta L, and this is X. Here, this is L0, and this distance, it's equal to delta L minus X. So delta L1, this is the first spring, and this is the second spring. Delta L1 become delta L plus X. It's equal to 10 plus 5 equal 15 centimeter. Delta L2, it's equal to delta L minus X. It's equal to 10 minus 5 equal 5 centimeter. Then potential energy, it's equal EPE 1 plus GPE 1 plus EPE 2 plus GPE 2. GPE in both equal to 0. So EPE 1 equal half K delta L1 square plus half K delta L2 square. Therefore, it's equal to half times 25 times 0.15 square plus half times 25 times 0.05 square. We obtain the potential energy equal to 0.3125 joules. This is the potential energy. This is the part 2. Part 3, M being in I, this I, we release it without speed, so Vi it's equal to 0 meter per second. This is part 3. Determine the speed factor of M when it goes for the first time by O. We have friction equal to 0, so mechanical energy is conserved. Then mechanical energy at O, it's equal mechanical energy at I. The mechanical energy at O is equal to kinetic energy at O plus EPE at O equal kinetic energy at I plus EPE at I. Kinetic energy at O equal half MVO square plus EPE at O, we calculate it at part 1, it's equal to 0.25 equal kinetic energy at I, it's 0 since without speed, plus EPE at I, we calculate at part 2, it's equal to 0.3125. So VO it's equal, we obtain equal 0.56 meter per second. M and M passes through O for the first time in the negative direction. So V0 vector it's equal to minus 0.56 I vector meter per second. Exercise 10. A solid S M equals 0.6 kilogram. We have M equals 0.6 kilogram. Launched with speed V0 following an inclined plane of an angle alpha relative to the horizontal as shown in figure A. In figure B, the curves of mechanical energy ME and gravitational potential energy GP of S depending on the x position of S. This is x and this is the energy. We have mechanical energy and gravitational potential energy. The reference level of the gravitational potential energy is the horizontal plane passing by O. Take G equal 10 meter per second square. Part 1. The graphs show the mechanical energy of the system is not conserved. Justify. We observe that the graph of the mechanical energy is decreased from 3 to 2 joule. So the mechanical energy is not constant, is not conserved. So mechanical energy is not conserved since the curve is not a horizontal line, not constant, it's decrease. Part 2. Pick out the potential energy of the system for x equal 3 meter. For x equal 3 meter, the potential energy it's equal to 2 joules. For x equal 3 meter, GPE equal 2 joules. Deduce the kinetic energy of the system for x equals 3 meter. We have for x equals 3 meter, the mechanical energy it's equal to 2 joules. And we know that kinetic energy it's equal to mechanical energy minus GPE. So the kinetic energy it's equal to 2 minus 2 equal to 0 joule. So the kinetic energy at x equals 3 meter it's equal to 0 joule. Part 3. Find alpha. We have GPE equal mgh. This is alpha and this is the object. This is h and this is the abscissa x. Apply sine alpha, it's equal to opposite side over hypotenuse side. The opposite sides of alpha it's h, so sine alpha equal h over the hypotenuse it's x, so h equal x sine alpha. Then GPE equal mg x sine alpha. For x equal 3, GPE equal 2. Then 2 equal mass 0.6 times 10 times 3 meter times sine alpha. We obtain sine alpha equal to 1 over 9. So applying sine minus 1, shift sine 1 over 9, we obtain alpha equal 6.4 degree. Part 4. Calculate the initial value of kinetic energy. We have kinetic energy at t equals 0, it's equal mechanical energy at t equals 0 minus GPE at t equals 0. the mechanical energy at T equals 0, it's equal to 3, minus Gp at T equals 0, it's 0. So the kinetic energy at T equals 0, it's equal to 3 joule. Deduce the value of V0, kinetic energy equals 3 joule. So have mv0 square equals 3. Then V0 square, it's equal to 2 times 3 over 0.6. We obtain V0 equal radical 2 times 3 times 0.6 equal 3.16 meter per second. Part 5. The non-conservation of mechanical energy is due to the friction force between us and support. Calculate the magnitude of this force, supposed force of constant intensity. Delta ME, it's equal to sum of work of non-conservative force. The non-conservative force, it's the friction in this question. So mechanical energy final, it's at x equals 3, minus mechanical energy initial at x equals 0, it's equal to work of friction. Then it's equal to 2 minus 3 equal minus f times x3. So minus 1, it's equal to minus 3f. Then friction equals 0.33 Newton.